Okay, let's take a look at another equilibrium problem. Here I have some kind of beam that is wedged into a corner and is held by a string. And we're going to assume this is the wall and the floor. There's no friction. We're going to assume there's no friction. And so the first thing I want to do is draw my forces. So of course I've got tension here, gravity pulling from the center. And here, the two corners of this beam, one's touching the wall, one's touching the floor, there's going to be normal forces on each of these. So there's going to be a normal force going this way, which I'm going to call FW for the wall. And this one I'll actually refer to as the normal force. But it's the normal force from the ground. This is the normal force from the wall. And so then, next thing to do is set up Newton's second law. I can start with my x forces. I have two. So this is going to be that Ft minus Fw equals 0. And I can deal with the y forces. This is going to be that Fg minus Fn equals 0. And for both of these, this is equilibrium. They both equal 0. So I could have said Fw minus Ft equals 0. Or Fn minus Fg equals 0. It doesn't change anything. The formulas are still equally valid. This is just how I chose to do it. But this is Newton's second law, both the horizontal and the vertical. Now the next step for solving these kinds of problems, because probably this isn't enough to solve the problem, whatever it is you're looking for. So you need to set up your torque equations. So the next part here, let's set up the torque equation. I'm going to start with down here. Okay. So I'm doing sum of the torques, and I'm choosing at, say, Fw. Now, Fw and Fn are essentially acting at the same point, so they're both at this rotational axis, so neither one is going to exert a torque about this rotational axis. Their lever arms are both 0. So I only have these two. So I've got the torque due to gravity minus the torque due to tension. And you can see these are opposing each other, these torques, because gravity would want the beam to rotate clockwise, but tension wants it to rotate counterclockwise. So they are opposing each other. Here we go for this torque. Okay, now let me just remind you, I'll write it down here. Torque is the force times the lever times the sine of the angle between the force and the lever. So coming back up here for the torque due to gravity, that's going to be Fg. The lever, it's going to be half the overall length. So this beam has a length of, say, L, so this is half the length, so this would be, its lever is L over 2. And then the sine of the angle. I need the sine of the angle between Fg, which is vertical, and the lever, which is parallel to this beam. Okay. Well, here we have the angle between the beam and the horizontal. That's theta. So that means that it's kind of a bad choice here calling this theta and theta. We're stuck with it. Anyway, so using this angle, which is for my actual problem too, let me just call this theta 1, just to differentiate it from this general angle. Okay, so this theta 1, so this is the angle to the horizontal, but I really need the angle between the lever and Fg, so that's going to be the sine of 90 minus theta 1. And that's going to have to equal, now my torque due to tension is going to be Ft. It's the lever is the whole length of the beam, L. And that's going to be the sine. Now here, I need the angle between the lever, which is again parallel to the beam, and the tension, which is horizontal. So this angle here this is just geometry. What is it? Opposite interior angles or something like that. But because this is horizontal, this is horizontal, these are parallel lines. But anyway, this has to be theta 1. So this is just the sine of theta 1. So there's one torque equation right there. Now I can choose, again, a different rotational axis. I could choose to go, let's do the sum of the torques at FG. Okay, so if I'm doing the sum of the torques at FG, this is now my rotational axis. Okay. So I'm going to have the torque due to tension. Now, tension wants it to rotate, if this is the rotational axis, tension wants it to rotate counterclockwise. And in fact, so will FW. FW wants it to rotate counterclockwise, but Fn wants it to rotate clockwise. So I would do the torque due to tension plus the torque due to the force from the wall minus the normal force from the ground. That has to equal 0. Okay, now I set up my, now I can go in and plug individually. So for tension, it's the force of tension. The lever is now half the length, but it's still the sine of what I'm calling theta 1. For the wall torque, so that's Fw, it is also L over 2 away from the rotational axis, because again, the rotational axis is right here in the middle where Fg is acting. It is also acting horizontally, and so it's also going to have an angle of theta 1 with its lever. And then for the normal torque, the torque due to the normal force, that's going to be Fn, again, L over 2, but this is acting vertically just like Fg was, and so it's the sine of 90 minus theta 1. And that's the torque equation. I can do one more torque equation. Sum of the torques, my last remaining point is up here at Ft. And so we're going to have, let's see, we're going to have the torque due to gravity. Okay. Now gravity, if I'm up here, gravity wants, if this is the rotational axis, gravity wants it to rotate counterclockwise. Okay. And so does Fw. Fn wants it to rotate clockwise. So the torque due to gravity and the torque due to the normal force from the wall are going the same direction. Torque due to the normal force from the ground is going the other direction. So that's why I'm subtracting it. So now we just set up our formula. So Fg, which is L over 2 away from the rotational axis, which is up here. And I already know that's a vertical force, so again, it's going to be 90 minus theta 1, okay, plus this is going to be Fw. It's L away, so L, and it's just the sine of theta 1. And that has to equal, and then I do the Fn, and Fn is going to be Fn times L times the sine 90 minus theta 1. Now all I'm doing here is just reiterating the approach, showing what you have to do. You have to draw your force diagram, and you need to be precise in where you draw the forces. You have to set up Newton's second law. You have to set up torque equations. Now, there might be the odd problem you don't have to set up Newton's second law. You can get away with just a couple of torque equations. Or maybe there's the odd problem where we've already solved problems where we don't need the torque equations, right? We can just use Newton's second law. But the problems in this unit, generally you're going to have to set up torque equation. In fact, I can guarantee you're going to have to set up at least one, probably two torque equations, and often you're going to need Newton's second law. This is the approach we're using. Yes, there are other things you have to do. Obviously, you've got to be able to stick in some of the other formulas we've learned, such as how to calculate FG. We've got a general formula for that. And there are other just standard algebra techniques that you will need to use as you're going through and solving these. But this is the approach, and that's what I'm trying to show you in this example and the other example that I posted in the homework. Obviously, if you have any questions, as always, contact me. If you have any questions about this or any of your problems, contact me, email me pictures of your work. Happy to help.